Okay, so what we're going to be going over today is now kind of the last third of this unit. Okay, Newton's second law basically is more than half of the unit because there's so many applications. Okay, and we've done now friction. Okay, we've looked at how friction works. We've done some problem solving involving friction and Newton's second law. We've done Newton's third law. So we're kind of all done with the forces part, for at least just the forces. Now, what we're going to be looking at is how the forces can do work. Okay, so what we have to review is kind of the basics of work energy theorem from Science 10. Okay, now work energy theorem is probably the most important concept in physics, at least in high school. Okay, because it's going to transfer over into physics 30 as well when you start looking at electromagnetic forces and the work that they can do in moving charged particles. Like, it just keeps coming back. Momentum and energy is your first unit in physics 30. There's a ton of work energy theorem stuff in that as well. Okay, so work energy theorem is kind of this overarching concept that just keeps popping up in lots of different topics within high school physics. So, first thing we have to understand is what work is. Okay? The truest definition of work is to change the energy of an object or system. Okay, so very basically, work is a change in what kind of energy? Could be kinetic, could be potential. When we combine those, we get, starts with M, mechanical energy. Okay, work is a change in mechanical energy. Okay, in the same way that heat is a change in thermal energy. Okay, they're both changes in energy. So work, okay, is a change in mechanical energy. So that's a triangle, delta. Okay, change in mechanical energy. So that's something you would have learned in Science 10. Now we calculate mechanical energy by adding the potential energy and the kinetic energy of that object or system. Okay, so the mechanical energy is the sum total of kinetic and potential energy for an object, or a system. Okay, everybody all right with that? Now, in Science 10, you may have also looked at the relationship between force and work and discovered that they said that work is not only a change in mechanical energy, but it was also force times distance. Okay? That means if I exert a force on something and it moves through a distance, I'm going to do work. I'm going to change the energy of either that object or the system it's in, or both. Okay? If I push something and it moves, but I don't change its energy, have I still done work? I have. Just not on that object. I've done work on, not myself. Let's think about this. Let's just look at this desk here, okay? And if I pull it without lifting it, okay, like so, if I lift it, I'll change its potential energy. Agreed? Okay. If I increase its speed a whole bunch, I'll be increasing its. Okay. If I just drag it at a constant velocity, then I'm not changing either one of those. Everyone okay with that idea? Okay, I exerted a force over a distance, but I didn't change the energy of the desk. Did I still do work? How do I know? Okay, it moved, but I didn't change its energy.
So how to overcome friction.
Okay, and what was the evidence that I did that? Sound. Is sound a form of energy? Where did it get the energy for the sound from? Me. Right? The desk would not have dragged and made noise if I hadn't done work, moved it. Okay? So I still did work. I just did work on the surroundings of the desk, not the desk itself. Okay? I didn't change the energy of the desk, but I did change the energy of the surroundings. I added some sound to the surroundings, probably a little bit of heat to the surroundings, and I may have worn down the little plastic feet on the bottom of that desk a little bit. Okay? All of those things would count as having done work on that system. Are okay with that? Okay, and depending on the situation, work and energy can be equal. And that's because of this statement right here. Work is equal to the change in energy. So if I start out with an object that has no mechanical energy, and I do work on it, its new energy will be equal to the work that I did, because work is a transfer or a change in mechanical energy. All right? That's all stuff that hopefully seems somewhat familiar from Science 10 physics. Okay? Hopefully. Okay, so strictly speaking, work is done if a force is exerted through a distance. Okay? That's where we get that work is force times distance formula from. So force and displacement are the essential elements of work. So if I just push on this wall, I feel huge. Okay, so if I push on this wall, and I push and I push and I push, I'm exerting a force, but am I getting any distance? No. Okay, am I doing any work? Well, not on the wall, okay, because the wall is not gaining any energy. Maybe some energy is going to the surroundings, okay, but I'm not doing any work on the wall because there's no distance. Okay, I'm not changing the energy of the wall. Everyone okay with that? Okay. Why would I get tired? I'm exerting force, but I'm only going to get tired by exerting a force if I expend energy. So somewhere there's energy going, right? I'm losing energy to something. I'm just not doing any work on the wall. This goes back to I'm going to transfer energy to the surroundings. Okay, that's when mechanical energy turns into other forms of energy, sound, heat, okay, things like that. Okay, in a simple example, your car stalls and you need to push it. Okay, so you're pushing it off the road. You're exerting a force over a distance. It'd be pretty easy to calculate the amount of work that you do. Okay, as long as you know what force you exert and how far the car goes, you can calculate the amount of work done, okay, in pushing the car. All right. So in this one here, the constant force points in the same direction as the displacement. Okay, and so we use this formula here. Now, this is a little different than what you learned in Science 10. Because in Science 10, you were told work equals force times distance, and it was as simple as that. Okay, it's not as simple as that, but it's not a whole lot more difficult either. Okay, it's just in Science 10, you never worked with angled forces. Okay, so the force was always in the same direction as the movement. Okay, in Physics 20, we know that forces don't always act in the same direction that the object moves. Okay, if I push on that car, and instead, like the way this guy is drawn on here, it doesn't look to me like he's pushing straight forward. It looks to me like he's pushing down and forward, like this. Okay, well, that means that not all of the force he's exerting is actually doing any what? Any work. The car isn't moving up or down. The car is only moving that way. So I only need the horizontal component of that force, because only the horizontal part of that force is actually causing any changes in energy. Everybody follow me there? Okay, so if I want to calculate that side of the triangle, it would be adjacent to the angle here, and the force I exerted would be the hypotenuse. Agreed? All right, that's where we get this formula from. Okay, the force times the cos of the angle gives me that side. Okay, it gives me the adjacent side, the side that's actually doing it. And the same would be true if I lifted this desk a little bit before I dragged it forward. Okay, the vertical part of my force is not really doing any work. Okay, the whole desk didn't move upwards. Okay, but I am pulling it to the forwards or backwards of the desk. Okay, and as a result, okay, I'm doing some work in that direction. But only the horizontal part of my force is actually changing any energy. Okay. Everybody all right with that idea? It doesn't come into play very often, but once in a while you'll have to put in the angle. Most of the time the forces we use are in the same direction as the work being done. Okay, now, weird thing. We talked about all this angled stuff, and then I'm going to say to you, by the way, work and energy are both scalar quantities. So then why does direction matter? Well, because I still have to find force. Force is still a vector quantity. Okay? I'm doing work only in this direction. I need to make sure I use the amount of force that's actually doing work in order to calculate the work. Okay? All right, so work and energy are scalar quantities. So I would never put a direction on a number that ends in joules. Okay? The reason being is energy can be used to do work, any kind of work, in any direction. Therefore, energy itself doesn't have a vector. All right. the units of work are in Newton meter. Okay, and we can see that because the formula to calculate work is force times distance. Units for force are newtons, units for distance are meters, Newton meter. Joule. Okay, you can write Newton meter if you want, but we always use joule, okay, as the units for energy. Right, so joules, okay, that's actually a kilogram meters squared per second squared. Okay, because a newton is a kilogram meter per second squared. We're multiplying by another distance, so we get kilogram meters squared per second squared, which is a joule. Okay, now these girls here are pushing on this rock. It's big. They can push on it all they want. That rock ain't gonna budge. Do they ever do any work on the rock? Okay, now, as we were saying before, it's often the case that a force is exerted in a different direction than the movement that actually occurs. And we looked at a bunch of those situations the other day. Okay, that means then that not all of that force is actually doing useful work, and we would have to figure out what component of that force is actually doing the work, and that's where this F times the cos of theta thing comes in. So we've already talked about that, but that's just kind of a diagram to show you what I mean by that. Okay? If I'm pulling this luggage carrier, I'm exerting a force this direction, but only this part of it is actually making the suitcase carrier move and moving in that direction. Right? So little things like that are things I'll need to remember. Okay, so if we look at this one, this is a very simple example here. Find the work done by a 45 Newton force in pulling a luggage carrier at a 50-degree angle for a distance of 75 meters. All right, so we know that work equals F cos of theta times d. We know that this force here is 45 newtons, but the luggage carrier doesn't go that way. The luggage carrier goes this way. So I need to find the force that is acting in the same direction as the displacement is going. Okay, so that means I go 45 newtons times the cos of 50 degrees, the angle they gave me, and then I multiply that by the distance, 75 meters, and I get that I have done 2.17 times 10 to the 3 joules of work. Now, that could look like one of two things. It could look like me accelerating the luggage carrier the entire 75 meters and increasing the luggage carrier's what kind of energy? Kinetic energy. Okay? Remember, potential is height. That would involve me lifting the luggage carrier, which I'm not doing. Okay? It says here the luggage carrier is being pulled along the floor. Okay? So that could mean that I accelerate the luggage carrier for 75 meters. Okay? That would mean that I started at rest and I get to some final velocity. Or it could mean I pull the luggage carrier at a constant velocity, and most of my, or all of my work is used to overcome what? Friction. Okay? Because if I pull that case at a constant velocity, then I'm not changing its kinetic energy. I'm not changing its potential energy. But I still did work. Okay? If I expended energy, it had to go somewhere, and it probably would have been to overcoming the force of friction. So it would have been work done against friction, and the evidence of that would be sound, heat, okay, and things like that. Right? So those are the two situations that could happen as a result of this. Now, one step further. If it's situation one, where I accelerate the luggage carrier, okay, could I figure out how fast I get the luggage carrier going? I could, as long as I know what about the luggage carrier. Don't need time. Mass. Yeah, I have to know the mass of the luggage carrier. I mean, think about it. If I am carrying a luggage carrier that just has a tiny little carry-on size suitcase on it, okay, I'm going to get that going a lot faster than I am if I'm carrying like 5 giant suitcases. Okay, everyone follow me on that? Same amount of work, but the end result would be that the big suitcases aren't going to be going as fast as the little suitcase would, okay, because same amount of work on bigger mass. All right, so we said then that work could be changing the mechanical energy of the luggage carrier. Let's just say that the luggage carrier is 20 kilograms, because that's about the biggest you can put on a plane, 50 pounds. Right? Okay, so 20 kilograms is the mass of my suitcase. And the work I've done, which I already calculated to be 2.17 times 10 to the 3 joules, okay, is going to equal the change in the mechanical energy of the suitcase. Now, I'm not changing the potential, I'm just changing the kinetic energy. All right, from Science 10, how do I calculate kinetic energy? On your formula sheet, how do I calculate kinetic energy?
Kinetic energy equals half of mass times velocity.
Right. Yes. Okay, 1/2 mv squared. Okay. I want to find the change in the kinetic energy. So we're going to say I started from rest and got to the speed I'm looking for. Right? So if I want to find the change in something, that means I'm going to take the final and I'm going to subtract the initial. Okay, since I started from rest, how much kinetic energy did I have initially? 0. So I can simplify. All right, so this is my work, and it equals the change in energy, which happens to be my final kinetic energy because I didn't have any to start with. Everybody following my logic there? Okay, I'm going to do this much work. My final kinetic energy is going to be this much. So 2.17 times 10 to the 3 joules equals 1/2 times the mass of the luggage times the final speed of the luggage carrier squared. Can I find the speed of the luggage carrier? Yeah. Okay. What do I do with this? What do I do here to get df by itself? Divide by half of m, and then what? Square root. Okay, this might look a little bit familiar. It's kind of like your roller coaster questions that you would have done with conservation of energy last year. Okay. All right, so I've got that number there. That should allow me to calculate the final speed of the luggage carrier. Okay, so half the mass, which you said was 20, right? So we'll just divide that by 10. Okay, I'm pretty fast because I'm going to be pulling that luggage carrier at 15 meters per second, which I don't think I can run that fast anymore, maybe in my youth, but not carrying a luggage carrier. Okay, so there it is. Everybody follow what I mean here by work being a change in energy. Okay? In this case, it changed the kinetic energy. Okay? In other cases, it can change the potential energy. So if I lift something from the floor and set it on a desk, okay, then I've changed its mechanical energy. I've changed its potential energy. Everybody okay with that idea? Right. In Science 10, you only dealt with work energy theorem questions where you changed either kinetic energy, like what we just did here, or potential energy. That would be lifting something up. In Physics 20, we're going to deal with problems where both change. Actually doesn't make it any harder. We just have to keep track of both compass. Okay? All right. Doing bench press. Okay? Doing bench press involves doing mechanical work. Okay? Changing the potential energy of the barbell. We don't want to change its kinetic energy very much. Okay? If you change the kinetic energy of a barbell when you're doing bench press, you're not doing the bench press very well. Okay? You want to lift it at a constant, slow velocity to your highest point, and then you want to lower it back down at a constant velocity back down to your chest or onto the rack. Okay? One or the other. But you do not want to just go push and then drop. Okay? Because then you get nothing out of the exercise. The longer you are exerting the force for, the longer your muscles work and the more benefit you get out of the workout. But I see people do that wrong all the time. They're just all about getting the weight up there and then like sweet, just drop it back down. Okay? You're only getting half the workout when you do that. Okay? Now, we want to determine the work done on a 710 Newton barbell. Okay, now if I give you the barbell in newtons, what have I given you? Its weight. Okay. If I want to lift the barbell, how hard do I have to push? Well, actually, if I want to get it moving at a constant velocity, the net force would be 0. So I have to push with 710 newtons. All right, so the force I have to exert to lift this thing at a constant velocity is equal to its weight, 710 newtons. Okay, I'm going to lift it 0.65 meters. Okay, so work equals force times distance. And what kind of energy am I changing about this right now? I'm moving it at a constant velocity, but I am lifting it. I'm changing its potential energy. Okay, what force am I working against? Okay, is that how we calculate the force of gravity? Okay, so force of gravity times distance. Is that the same as this formula? Yeah, because a vertical distance is a height. Do you recognize that formula? That's how you calculate potential energy, isn't it? Okay, the potential energy formula is force of gravity times distance. All right, let's figure out how much work we're going to do here. 710 newtons times 0.65 meters. Okay, so to lift that barbell will require 461.5 joules worth of energy. Now I have a giant 710 Newton barbell hovering above my head, and it now has the potential to crush me. Because what have I done? I gave it potential energy. Okay, that was dumb. I just lifted something really heavy up over my head. Okay? I did work on it, and I gave it the potential to hurt me. So, if I let it come back down, like by dropping it, how much work can it do on me? How much exactly? 461.5 joules. That's significant. That could change your shape in an undesirable way. Okay? So, if I want to lower it safely, I need to let it do 461.5 joules worth of work. But I have to let it do that slowly. Okay? That's why we lower our weight slowly, hopefully. Okay? Now, that work from the barbell's point of view is going to be what? Positive or negative?
Positive.
Negative. Okay? When I lifted the barbell, from the barbell's point of view, it gained 461.5 joules worth of energy. Right? It didn't have any energy sitting on my chest. Okay? But when I lifted it, it did. So from its perspective, that was a gain or a positive work. When I lower it back down, it's going to lose that energy. So that's negative work. And that negative work is going back to me. I still have to do work to lower the barbell. I have to absorb the work, okay, that the barbell wants to do. Okay? That's why you want to lift slowly and lower slowly. It's twice the workout. Okay? You just let it come back down. You don't exert that same force. You let something else catch it, maybe your spotter or your rib cage. So pulling up your rib cage. Okay? Everybody follow me there? So I just said work and energy are scalar, and then I said work can be positive or negative. Is that contradictory? Actually, it's not. I never said the positive and negative were about direction. I said it was about whether the work was being gained or lost. Okay? So work can be positive or negative, but it's a matter of perspective. Was the work done on you, or did you do the work? If I do the work, from my perspective, that's negative. Because I'm now lost or transferred away that much energy. Something else has gained it. Okay? That's where the law of conservation of energy comes in. You can't create energy, you can't destroy it, but you can transfer it. Okay? So when I do work, I transfer energy away to something else. That's a loss of energy for me, it's a gain of energy for something else. Okay, so if we're looking at this, okay, we just said we did work as force times distance, but if we really look at it from like a vector perspective, Okay, I went F cos of theta times D. Okay, but theta was 0. Okay, because my force and my direction were in the same direction. What's the cos of 0? 1. Now, when I lower the barbell back down, I exert a force upwards, but the barbell moves downwards, which is how many degrees? 180. What's the cos of 180? -1. So if you actually plug this into your calculator, you actually get the positive and negative answers you're supposed to get when we were talking about how one is gain and one is a loss of energy. Okay, so that's what we just talked about there. Okay, and here the cos of 180. Okay, so we do negative 460 joules when we lower it. Okay, positive 460 joules when we raise the barbell. Okay, so things we have to remember about work and energy. Okay, in order to do work, you have to have energy. Okay, this isn't like a credit card. Okay, work energy theorem doesn't work like a bank. You don't got the money, you don't get to spend it. Okay, so in the case of work energy theorem, if I want to lift something, it's going to require 200 joules worth of energy to do it. I have to have 200 joules worth of energy. Okay, otherwise I won't be able to do that job. Does that sort of make sense? Okay, so you have to have energy. Okay, in a perfect world, okay, it's always going to be 100% transfer. In the real world, it's never that way because nothing is 100% efficient. Okay, but we're going to treat everything like it is. Okay. All right. So things to remember here from Science 10: our kinetic energy formula, our potential energy formula. Okay, work is a change in energy. Okay, and in addition to that, these formulas here: work equals F cos of theta times D, and that work, okay, well, we got is the change in energy there, and that mechanical energy is kinetic plus potential. Okay, those are all things we have to remember. They're not all necessarily on your formula sheet. Okay, some of those things you just have to remember. Questions on that? Is that ringing a bell a little bit from Science 10? Anyone still need that? All right, so we're going to go over a few examples here, but not that one. Okay, let's have you guys try question number 1. Okay, it's a work is F cos of theta times D type of question, right? It's pretty straightforward. You're basically just plugging in the numbers here, right? So I'm going to give you a few minutes on question number 1. If you finish 1, try number 2. Okay, it's basically the same thing, just with a little manipulation. Okay, so I'll give you a couple minutes on 1 and 2 here. Okay, so for question number 1, basically we're just plugging in numbers into the formula. Okay, they're telling us that the sled is being pulled along the surface by applying a 620 Newton force 42 degrees above the horizontal. Okay, so we've got this. Okay, this angle here is 42 degrees. We're pulling with 620 newtons, but the box or the sled isn't going that way. Okay, the sled is going this way. So we need to figure out how much of this 620 newtons is actually changing the mechanical energy of the sled. Okay, to do that we go work equals F cos of theta, so that'll give us our horizontal component, multiplied by the distance, okay, which they told us was 160 meters. All right, so we're going to take our 620 times the cos of 42 and multiply that by 160 meters. Okay, and that should give us our 7.37 times 10 to the 4 joules worth of work. Okay, everybody all right with that one? Yes. Okay, number 2 is basically the same thing, except this time they want us to manipulate it and find the force instead. So they're telling us 9,600 joules worth of work is actually done. It's over 25 meters, and the angle is 30 degrees. All right, so we have that work equals F cos of theta times D, and we're just looking for the force. So we divide both sides by cos of theta times D. Okay, and that'll give us our force. So we'll take our 9,600 joules, divide that by the cos of 30 degrees times 25 meters. Okay, and when we do that, we should end up with our 443 newtons worth of force in joules. Okay, we're going to skip number 3, but I want to talk about number 4 here quickly. Okay, so you have a bungee jumper with a mass of 60 kilograms leaps off a bridge. They're in free fall for 20 meters, okay, before the cord begins to stretch. How much work does the force of gravity do on the jumper before the cord begins to stretch? Okay, what kind of energy do they have standing on the bridge? They have potential energy. Okay, they want us to find out how much work gravity will do over 20 meters. Is gravity a force? Okay, so can I still do this? Yeah, the height they fall is the distance over which gravity acts. But remember, we said since it's gravity that's doing the work, really all we're doing is calculating their potential energy when they were on the bridge. Okay, that's really all we're doing here. Okay, when you calculate the work done by gravity, you're calculating the potential energy that the object had. Okay. So we just take m times g times h, and we're going to get 1.18 times 10 to the 4 joules worth of energy. Okay, now how much work is the bungee cord going to have to do? That much. Okay, that's how much work gravity does. Okay, in making them fall the 20 meters. If we don't want to smash into the ground, then we need the bungee cord to take away all of that energy. Right? Change the cord's shape by stretching it and slowing us down. That sort of makes sense? It's a conservation of energy thing. I don't want to have any energy when I get to the ground. Right? I want to have zero kinetic, zero potential, and I don't want to get hurt. That means the bungee cord has to take away all of my energy. And it does that by allowing me to do work on it. That work comes in the form of stretching the bungee cord.
So why would you go all the way back up to the bridge?
Because it's not 100% efficient. Right? But it's going to make noise and stuff like that. If it was 100% efficient, you would fly right back up and land back on the bridge. Nothing's 100% efficient. And it would also never end. Right? There'd be no way to stop you if you didn't lose energy at each time it was converted. You'd boing, 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 the whole time. Okay. So, want to look now at an example where both kinds of mechanical energy both kinds of energy are being changed. The potential energy of the object as well as the kinetic energy of the object. So I want you to write this example down with the diagram. Okay, give you a minute or two for that, and we're going to walk through how this type of work energy theorem problem works. It is very similar to what you would have done last year, except it's going to involve changes in both potential and kinetic energy. Okay, so the first thing is we have to look at this situation and ask ourselves, is there work being done here? Okay, if work is being done, that means the mechanical energy, either kinetic or potential or both, are going to change for the object in question. So in this question, we start out with a box at the bottom of a ramp. How much potential energy does something have at the bottom? None. Okay, it's moving at 1 meter per second, so it does have some what? Kinetic. All right, so it's got some kinetic, that means it's got some mechanical energy. When we're all done, this thing is now at the top of the ramp and moving faster than it was at the bottom. Do I do work in this situation? Yes. Not only do I make its kinetic energy go up, but it's going to be at the top of the ramp at the end, which means I also change its potential energy. So there's definitely work being done in this question. So work is a change in mechanical energy. Now, quick review. How do I calculate mechanical energy? What two things do I add together? Potential and kinetic energy. All right, so I'm going to have to keep expanding this formula out. I'm going to make it longer and longer and longer, but it's always going to say the same thing. So change in mechanical energy means the final mechanical energy minus the initial mechanical energy, right? Because change is always final minus initial. Okay, now a minute ago you just told me I calculate mechanical energy by adding potential and kinetic. So I'm going to expand this out again and say the work done here is going to be, potential final plus kinetic final. Okay, we said mechanical energy is the sum of potential and kinetic. Okay, so I'm still saying the same thing here. Okay, minus the potential initial plus the kinetic initial. So this is calculating my initial mechanical. This is calculating my final mechanical. If I subtract them, that will calculate the change in mechanical, which is equal to work. Everybody all right with that idea? Yes? Okay. I'm going to expand it again. It's going to get even bigger. Okay? All right. So work then is going to equal m times g times h in this, final. Okay? So this is my final potential energy, right? This is how I calculate potential energy. And this is going to be my final height. Okay? Plus 1/2 mvf squared. Here's my final kinetic energy. 1/2 times mass times the final speed of the box. Minus the same thing initially. Didn't seem nearly that involved when I wrote W equals delta EM, did it? Okay, there's a lot involved here. All right, do I know most of these numbers? Yeah, okay. I know the mass. They told me what the mass was in the question. Okay, they said it's 1.2 kilograms. They told me the final speed. They told me the final height. Okay, we know it's at the bottom initially, so we know the initial height, and we know the initial speed. We know all of these numbers except for work, which is what they want us to find. Okay, so can I plug in my numbers now? So we're going to have 1.2 kilograms times 9.81, because that's what G is, times the final height, 0.850 meters. I'm going to add that to the final kinetic energy. So that'll be 1/2 times the mass, okay, which was 1.2, times the final speed, which was 4 squared. Okay, then I'm going to subtract, well, what's my initial potential energy? 0. Do I need to bother going mass times gravity times 0? It's going to be 0, so I'm not going to do that. But I do have some initial kinetic energy. So 1/2 times 1.2 times 1 squared. Okay, because they did say at the bottom of the ramp it was moving at 1 meter per second. Okay, so now I should be able to calculate how much work is done. Okay, it'd be the difference between the energy at the bottom, that's this number here, and the energy at the top, that number. So 1.2 times 9.81 times 0.85 plus 0.5 times 1.2 times 4 squared. All right, so there's the energy I have at the top of the ramp. But the work I do is the difference between that and the energy at the bottom. So I'm going to subtract now the energy I had at the bottom. 0.5 times 1.2 times 1 squared. Okay, so according to this, I've done how many joules worth of work? 19. All right, to get that thing from the bottom of the ramp to the top of the ramp required 19 joules worth of work. Perfect timing! Okay, have a good weekend, but not too good. Think about this and that'll make sure.